velik del svojega raziskovalnega dela je izvedla kasneje na Švedskem, kjer je sledila svoji nekakšni originalni raziskovalni poti. Torej, je svetovna pionirka na področju ultrahitre laserske znanosti, kjer so njene prelomne raziskave bistveno prispevale k razumevanju dinamike elektronov v atomih in molekulah. Njeno temeljno delo o generaciji visokorednih harmonikov je postavilo temelje za razvoj atosekundne znanosti, kot jo danes rečemo. Ta omogoča opazovanje gibanja elektronov v realnem času v izredno kratkih časovnih obsegih. Njeni dosežki ne vplivajo zgolj na temeljno fiziko, ampak odpirajo tudi raziskave v kemiji, v materialih in v fiziki. Torej, v zgodnjih 90-ih letih je sodelovala na področju izgradnje enega od ključnih laserjev, ki je danes v uporabi po celem svetu, tako imenovan titjan-safir laser, za katerega sva ugotovila, da imava zelo skupno pot. Torej, tudi v Ljubljani se je ta tehnologija razvila vsaj 30 let. Ona je bila pionir v razvoju tega in na osnovi teh odkritij je omogočila pač regeneracijo izredno kratkih atosekundnih sulkov. Njeno izjemno kariero potrjujejo števila priznanja, med njimi L'Orealovo nagrado in Nobelovo nagrado za fiziko leta 2023. Poleg znanstvenih dosežkov se profesor Lulje odlikuje z neprecenljivim prispevkom komentarjev z mladih raziskovalcev in pa spodbujanju žensk v znanosti ter mednarodnega sodelovanja. Torej, današnje predavanje bo naslov je A Journey to the Attosecond, and with that I'd like to give you the floor to Anne.
Good morning. It's a pleasure to be here. So I will try to tell you about this journey to the Attosecond time scale. And I will, can you hear me, or you want me to be?
If you can go behind.
Yes, then I move this.
Yeah.
Yes. Yeah. Is it better now, or now?
Thank you.
This is better? Yeah.
Thank you.
Okay, so I start here by showing you an arrow of time from the age of the universe to the attosecond. And you see that there are as many orders of magnitude from the age of the universe to the second than from the second to the attosecond. So it's really a very, very short time scale. And just to be clear, we will not talk about one attosecond, but more tens or hundreds of attoseconds. So you have a few time scale here, some time scale of humanity, the year, the day, the second, which is heartbeat, and then you have time scale for mechanical motion, for electronics, and now we come to the time scale of motion of atoms in a molecule, and then the time scale of electrons in atoms. In general, the lighter the particles, the faster they move. This is a picture of a molecule. Maybe you think that the atoms are just, they don't move, but they move a lot, they vibrate. And to capture the motion of atom, you need femtosecond pulses. 1 femtosecond is 10 to minus 15 seconds. And this was awarded the Nobel Prize in Chemistry to Ahmed Zival. And then if you want to capture the electron motion, you need attosecond pulses. And this was awarded Nobel Prize 2023 to Pierre Agostini, Ferencz, and myself. So So this is the outline of this talk. First I will give you a little bit background, and then I will talk about high-order harmonic generation, attosecond light pulses, and a little bit attosecond physics, what we do with these pulses. So the background is really the invention of the laser in 1960. Without invention of the laser, we could not have done this research. This is a picture of one of the first laser which was built. It's a ruby laser. You can see the ruby material here inside. And it was invented by Theodor Meinmann in 1960, based on light amplification by stimulated emission of radiation. This is the acronym of laser. And since this year is the International Year of Quantum, it's always nice to talk about Max Planck, actually, that really invented the concept. It was a theoretical discovery to explain the radiation of a black body, to describe the light in terms of quanta, photons. The invention of the laser opened new research areas. One of them is nonlinear optics. Here you have the experimental setup for the first experiment showing second harmonic generation, 1961, so directly after the invention of the laser. And what you have here is you have a laser, ruby laser, focused by a lens into a piece of quartz. And you analyze the radiation using a prism. And then you have a photon detector here. And you see two points here. One is the laser light, and the other is the second harmonic with the frequency equal to 2 times the frequency of the laser. So in this process, the atom absorbs 2 photons and emit another photon. So you can generate new frequencies of light using this phenomena. Another new research area was very fundamental, basic research. Study what happens when atoms are exposed to strong laser light. You have an atom here and being exposed to a strong laser field. And this was the thesis of my PhD in the 80s. It was done at the Commissariat à l'énergie atomique in France. The lasers that we used at that time, I should not move too much, were it's only this big research institute that could have this laser at that time. This was expensive. So, and I defended my PhD in 1986. So again, simple, we have atoms exposed to laser, and we look at what happens. We look at ions or electrons. Now I'm coming to the second part, high-order harmonic generation. Do you follow me? Yes? Okay. So at that time, I was a young researcher. I had been recruited almost immediately, half a year later, after my PhD defense at the same institute, Commissariat à l'énergie atomique. So at that time, we had the idea to look at the light that would be emitted when you expose these atoms to intense laser pulse. And at that time, we were thinking that we want to look at fluorescence light. We knew that in this interaction between atoms and laser, we create excited atoms, excited ions, and we want to know more by looking at the fluorescent light emitted by these atoms. So this is the setup, looks approximately the same as what I showed you before. We have a grating instead of a prism, but it's the same. and then a photon detector. And what did we see? We did not see fluorescence light. This is the beauty of experimental research. Sometimes you see things you do not expect. Instead, we saw a high-order harmonic generation of the laser field. You have here one of the first spectra obtained in argon gas and showing peaks. And these peaks correspond to the frequencies of the peak is equal to a multiple of the frequency of the laser light. So it's a high-order harmonics. For example, 31 here means that this is the 31st harmonic of the laser light. And what was very interesting is that the intensities of this high-order harmonics had an interesting distribution. If you plot the intensity as a function of order, you find that the intensities of these harmonics is approximately the same. And this was really, I think, the most important discovery in this experiment is the fact that, well, we found these very high order processes leading to the same, with the same probability. And this was going against the understanding at that time that you could use perturbation theory, where you write what is happening in the medium as a series of powers of the electric field. For a series to be valid, you need the different orders to be to decrease, and this was not the case. The intensity of these harmonics was approximately constant. So very high nonlinear process and non-perturbative. So if you are a bit lost here, let me first of all explain what we are talking about. This is a picture of the electromagnetic spectrum going from radio waves to X-rays. You have the visible part here in the middle. And through this process, we start in the infrared, and then you multiply by a multiple, by an integer, which can be quite high, and you end up in this extreme ultraviolet region of the spectrum. So it's above ultraviolet, and it's below X-rays. And in this region, the radiation is invisible to eye, and it's also strongly absorbed by matter. It's interact with matter. And we are working with vacuum chambers. I'm going to show pictures in a moment. And now, again, if you are a little bit lost, I'm sure you have heard about harmonics before in music. And by curiosity, this is a spectrum that you get when you play the violin. You play a certain tone. You get not only the tone, but actually many harmonics. And the number of harmonics that you get actually affect the clang of a music instrument. And for example, I heard recently that if you sing, I'm not going to sing for you, but if you sing, if you say ah, for example, and then you say oh, same note, what is the difference? Actually is the number of harmonics. Very, very interesting. So in both cases, we have a strong interaction here between the string of a violin and the bow, and here between the atoms and the laser pulse. However, here I'm talking about harmonics of light, optical waves, electromagnetic waves, while here these are acoustic waves, so very different type of waves, different frequencies. I'm also talking about coherent light by opposition to incoherent light. This is the light that you see around us, from the lamps, from the sun outside. It's because of spontaneous emission, which means that the atoms emit some waves in all directions, and anytime. It's called incoherent light. What we have is laser light radiations, coherent. The atoms emit waves in one direction and in a way where these waves are in phase, they act together. So they build up a big wave. Here as well, let me make a small analogy with music. You can imagine that this is an orchestra playing some music, and this is the orchestra before the concert has started. The instrument playing completely random, and this is the orchestra playing after the concert has started. They play together. It's not very good analogy, but it's a little bit to explain this what is meant by coherence. If I want to use a little more the physics language here, what we have is a phenomenon which is belong to quantum physics. We look at the emission from an atom to an intense radiation. This is described by a Schrödinger equation that you see here with an atomic potential and interaction between laser and atom. And that's the specificity of this process, is that this interaction is strong, is comparable to the atomic potential, to the what is making electrons being bound to the nucleus. So very strong interaction. But it is also part of electromagnetism, described by Maxwell equation, which can be simplified by a wave equation that you have here, where you have a medium which is polarized by the laser field, and you have a field which is generated in this medium. And again, you need to have this picture. It's important that all the atoms are working together in this process. This is called phase matching. Okay, so this discovery, which I have been talking about, was in 1987. We, of course, we study it, and in 1992 there was a huge progress in both laser technology, and also we build our own instrumentation. And here's a picture from this time of me together with my first PhD student. And we build this instrument that you see here. This is a little bit to tell you about the size of the physics that we do. We don't need a big instrument. We need a little more than something, a little laser like this. What you see here is shown here. It's basically what I showed you already. We have a lens, we have a laser, which you don't see, it's behind the wall here. And we have a gas jet coming from the tube here. We have some gas. And then we have some optics, which is in this chamber. So these are vacuum chambers. The pumps are below. And then we have here a photon detector. And this is also the time where there is really a fantastic progress in laser technology, with a new technique, which is called chirp-pulse amplification, led to a Nobel Prize to Gérard Mourou, Donna Strickland, a few years ago, 2018. And in Sweden, they are building the first terawatt titanium sapphire laser, using this technology and using a new material which is called titanium sapphire. This was really revolution in short pulse laser at the time. And in Sweden, somehow they decide to invest in this new technology and to build a new facility. And this is they ask me. This was also the beginning of European collaborations, networks. So they asked me to come with the instrument that I showed you just before, and my student to come to Sweden, to Lund, south of Sweden, to do some experiments, which we did. It was really very, very nice. This laser was really fantastic, and this laser was going to be the standard laser for this research during 20 years afterwards. So in this collaboration, I also met my future husband. This is how life can affect a career as well. So 2 years later, I moved to Lund. I was really helped by by the French Institute I belonged to in this process, 2 years to find a new job in Sweden. So they allowed me to commute and to get to still be employed in France, although I was living most of the time in Sweden. So very helpful. But then in the end, I became associate professor in 95 and then professor in 97. Okay, I'm coming to the third part. You still follow? This is okay? Yes? So what are attosecond light pulses? So let me explain to you the idea using a cartoon here. So we're going to do some mathematics together. So here I'm plotting 3 waves corresponding to 3 harmonics. It's only odd order because of symmetry. I don't want to explain here, but it's only odd orders. So you have the number of maxima here increases because this is higher frequency. Now we assume that these waves are in phase at a certain time, synchronized at a certain time. Because of the periodicity of the process, then a little bit later, actually half a laser period later, the minima will be at the same time, and then again the maxima, etc. So now we sum these different waves. And what do we get? We get actually a series of very short light pulses. We call it a train of attosecond pulses. Here you have constructive interferences. The waves here are pretty much synchronized. So here we get a big wave, whereas in the middle, the maxima and minima are not at the same time, so we have destructive interference, etc. So if you plot the intensity of these pulses, you get this train of attosecond pulse. And if you sum not only 3 harmonics, but let's say 10 harmonics, then you can get even shorter pulses of the order 100 attosecond or a few hundred attosecond. And this was the first time we were talking about this time scale. It was really a new time scale in physics. It was very exciting. At the same time, the question was, is this true? Are they synchronized at the same time, all of these harmonics? And actually, it's going to take us 14 years to be able to answer this question. And the answer of the question is going to be almost, not really exactly, but not too bad. Enough to have this very short light pulse, this interference effect leading to short light pulses. So here's the question. Are the harmonics phase locked? And one of the big steps in understanding and really trying to believe that, yes, maybe we had very short light pulse was an intuitive model of the interaction, which was proposed in 1993 by theorists, and which is summarized in this cartoon. So what you see in this cartoon is an atomic potential which is distorted by the laser field. That's why it's not symmetric like this. It's bent by the laser field. And this leads to the possibility for an electron in the ground state to tunnel through this barrier. Then the electron is driven away, and it's coming back and recombining, and in this process you have emission of a very short light pulse. And I have a kind of cartoon of this model, which is shown here. It's a small story called An Adventure of an Electron in the Laser Field, which can be represented by this. So you have an electron which is bound to the nucleus. It's a very strong force, otherwise we would not exist. It's good that it's like that. So the electron is in prison, and on the side you have the laser. It's a strong interaction, it's a strong laser. So this is a roller coaster. Okay, so what does the electron do? What do you think? Usually I tell this story to students and they give me the answer. So, well, the electron escape by a process called tunnel ionization, so this tunnel process. Then the electron is very happy, is coming down and up in the laser field. And this story is finishing badly. The electron is meeting on its trajectory the prison, which is open, and is falling and screaming out its energy, which is the light pulse. Okay, this analogy actually is not too bad if you think about forces and anyway. So that's the process by which you have this emission of very short light pulse. And in this model, you explain actually the process in the time domain. Through this process, you have emission of short light pulse, and you have a series of short light pulse. In the frequency domain, you have this high order harmonic generation. Now, 2001 was a very, very important year because this is really, even though with this theoretical model which I just showed, we were starting to understand more and more what was happening. Before you have really measured attosecond pulses, you don't know. So the experimental verification was very, very important. And as I said, it took many years to be possible. It was realized by my two colleagues that got a Nobel Prize with me, Pierre Agostini and Ferencross, in 2001. So the technique is called cross-correlation, and I can try to explain to you using my hands. This is kind of idea how the techniques work. So what is happening is that you want to, how do you measure an attosecond pulse? There's no detector. This is the shortest time scale ever. So how can you measure that? Well, what we do is we measure it with the help of the laser, which is the help of the optical cycle of the laser, which is almost as short as this attosecond pulse. So we sent these two into a gas of atoms and we look at ionization. And then we perform what is called cross-correlation experiments. So let me explain with my hands. You want to look at something, electrons in this case, which depends whether, so this is one attosecond pulse, and now this is the optical wave, the laser. So you want to measure the optical cycle okay? And you do a cross-correlation experiment. You measure, you send this to light to a gas, and you want to look at ionization. And ionization is going to depend on whether you are like this or like this. See the difference? And you vary the delay between the two here. So you look at how ionization depends on the delay, this or this. If your pulse is not short, but long, for example, like this, if you do this, there is no difference. Are you with me? No difference here. You don't see any difference. But if it's very short, then you see a difference. This is the principle of the measurement, very roughly described. A little political comment here. This field of research has brought a Nobel Prize to European people. This is not so often, only Europeans. I think this field of research has been very, very well helped by the European Union, by collaborations, by networks, later by ERC, that has made this field of research very strong in Europe. And here you have the kind of the first measurements of Attosecond light pulse in Paris, in Vienna, then in Lundu. The record at the moment is 43 at Attosecond, and this is in Zurich. So I'm really thankful to especially in the end of the 90s, beginning of 2000, we were meeting each other in Europe very frequently. We were exchanging ideas. We were also competing, but we were exchanging ideas, students. There was a very strong European effort, which I think is very good. This is a picture of modern equipment. Just to tell you again what it is that we talk about. This is a laser that we are using, an example of, this is called the optical parametric amplifier system. And then we need vacuum equipment to generate harmonics and to study them. The side of this vacuum equipment is like this. So it's not huge physics, it's still physics with small instrument. I'm coming to the end of this talk. I'm going very briefly to tell you what we are doing. And what is very interesting is that this is the time scale of electron motion in atoms and molecules. This is a picture of Niels Bohr's atom model, which you see everywhere when you Google about atoms. And if you calculate using this model from 1913, if you actually calculate the time of for an electron to rotate around the nucleus, it's 150 attoseconds. So for the lowest state. So it's the right time scale. Of course, this model is really not really what an atom is. This has been changed, I would like to say, by quantum mechanics. So this you cannot do. This is really, you have wave around the nucleus. One thing we can do is, however, is to look at the photoelectric effect or photoionization of atoms. When an atom absorbs radiation and is ionized, we start to be able to measure we actually are able to measure time for electron to come out, to propagate out of the atomic potential. So this is the photoelectric effect, which was discovered by Hertz, 1887, and explained theoretically by Einstein, 1905. So in this process, if we want to talk a little bit about quantum mechanics here, I think most people here think about this electron being emitted as a particle. It's going out and it's being detected. However, we know from de Broglie, 1924, that it's also a wave. And actually what our Attosecond techniques allow us to do is to determine, to measure the wave properties of the photoelectron. It's a wave, it has an amplitude and a phase. We can measure the phase thanks to our Attosecond technique. And if you know the phase and amplitude as a function of energy, you can do a Fourier transform and you will know the temporal dynamics of the process. Recently we have even gone a little bit further and look at the quantum properties of the photoelectron. I will show a picture in a moment. So let's start by how do we measure the wave property of a photoelectron. And here I'm looking at a very kind of famous process, which is where you have an electron, you have an ionization of an atom. I'm going to look at helium atom, very simple. Close to a resonance. Here, this is a resonance state. So this is a kind of a typical example of quantum mechanics, where you have two paths to the same final state here. So the electron can go directly here or via excitation to these states, and then it's called auto-ionization. So it's really a quantum interference process. How do we have access to this, the phase of this process? We use an interferometer. Here I'm a little bit more technical. So we use two harmonics here and an infrared laser it's a quantum interferometer where we can measure the phase of the photoelectron. And here's the result. We see a very nice interference effect. So with the wave is going up and then down, up again. And this is the phase variation, which is approximately pi across the resonance. And since we have now phase and amplitude as a function of energy, we can go into the time domain and really follow what is happening. We really look at photoionization in the time domain. And what you see here, this is a time frequency representation. It's called Wigner distribution. But what you see here is first we have direct photoionization. This is the yellow thing here, which is broadband, a little bit short in time. And then you have a strong interference effect here when you have blue and yellow. Blue means it's below zero. And then in the end, you only have this excitation followed by auto-ionization. Takes longer time and it's much narrower in frequency. So we can follow, thanks to our technique, we can really follow what is happening. I will just finish by showing a little bit what we are doing now. I'm not going to explain, this is more technical. This afternoon I will explain more. But we are, recently we are really looking at the quantum state of a photoelectron. In nature, you have, of course, nature is quantum and the microscopic part. And we have very often, you have entanglement, and we are trying to for example, ion electron entanglement, and we are really trying to look at the result of this entanglement on the photoelectron. It's not always coherent all the time. It's in the language of quantum information, it's a mixed state, and this is what we try to explain. I'm not explaining very much here, I'm just giving you an outlook. What is the next chapter in Attosecond science? This field is actually going into many directions at this time. It's impossible to know everything about what is happening. Of course, in atomic physics, atomic spectroscopy, in chemistry. In chemistry, the idea is to follow the electronic transition, which happens at the beginning of a chemical reaction. Condensed matter physics, same idea, to look at electron motion. There are some industrial applications, in particular to do imaging of integrated circuits. This is the right wavelength range in the extreme ultraviolet. And a little bit towards quantum, as I just showed you very, very briefly. This field has been created and driven by lasers and by this high-order harmonic generation process, which I described. However, now since 2 or 3 years, the free electron lasers have learned to produce attosecond pulses, and it's moving very, very fast. So they are producing attosecond pulses which have much higher photon energy in the X-rays, and in general much higher energy per pulse. So they are going extremely fast. They use the techniques that we have proposed and that we are using in a different regime, and they have fantastic results. So with that, I would like to thank you very much for your attention. And this is a picture of my research group in Lundu, and also some organization financing this research. Thank you very much.
Thank you very much for a very well adapted talk. I think we appreciate the detail as well as the historical perspectives. Thank you. I'd like to invite some questions from the audience, please. Maybe just a small one. When you explain this interference in helium ionization,
Yeah.
so can you go to that slide? You had this resonance which was beyond the ionization? Or?
Yes. It's 2s2p, for example. Yeah. It's above. Yeah.
So actually,
Yeah. I mean, we are looking at. We're not looking at the bound states. We are looking at electrons going out, because this is what we measure. But however, this can be affected in this case. Yeah. I did not give many details here, but for example, 2s2p in helium. Yeah.
I'm a chemist, so I'm interested if this could be used to monitor chemical reactions, or
Yeah.
the time scale.
Yeah, this is a question I often get, because chemists think this is much shorter time scale and then nothing happens in chemistry. The idea is really to look at what is called a charge migration by opposition to charge transfer. So it's kind of the very rapid electronic motion that takes place at the beginning, and this is typically for light-induced process. So I personally think that to extend, myself, I am an atomic physicist, and we have really we are developing the techniques using simple atomic system. But I think the big challenge of our field is really in this area, chemistry and condensed matter, is really to look at more complex systems, to find new ways to control, and I'm thinking about electronic transitions taking place at the beginning of a process. Yeah. And so Attosecond chemistry is not my invention. I mean, it exists, and I know it has been controversially, at least a few years ago, because chemists were not so happy, but I think now they are much more convinced. And this is really coming up, looking at biomolecules using these techniques. What is difficult is to interpret what is being observed, but process at the attosecond time scale are being observed.
Maybe I can ask a question. In your opinion, the progress of the field with free electron lasers, of course, has been very rapid. But do you see that the lab scale experiments have a future in the sense that that they're cheap, they're more accessible, but there's also other aspects. Maybe you can ask.
I think there is no problem. there is no real competition, and it's different sources, and we have the advantage to be a tabletop. And I think personally, I think this is an advantage to be actually at much lower photon energy, because this is where things happen in matter. For example, both are actually needed and interesting. So I think these are going to be very complementary, both by the type of physics you can do and by the type of facility. I mean, this exists only in at the moment in two. There are only two. It's in Fermi actually. They have attosecond time scale, and at LCLS. This is where they can propose some attosecond time scale. But it's coming very soon at LCLS and also other free electron laser places in the world. But again, this is only a few facilities, so you cannot do the same physics. That's my opinion.
The advantage, of course, of a tabletop is that you can repeat experiments very easily.
Yeah.
And it allows more in-depth
Yes.
research very often.
Yeah, and you can explore more things. Yeah.
Just a brief question. At some point, I remember you were telling us that you had a company that was making these phosphorates or the correlator. I think you briefly alluded to that. Still available?
Yes, not. This is more for diagnostic of laser pulse. Yeah, it's called Sphere Ultrafast Photonics. It's in Portugal, so making this diagnostic of laser pulse. So yeah, very very short pulses. Yeah.
It's still operational.
It has recently celebrated 10 years anniversary. So it's not startup anymore. It's called deep tech or something like that. But yeah, that's very nice. And this is something I have done really thanks again to the European Union with these POC instruments. Yeah.
Are there any more questions?
Maybe I get a stupid question, but you know I'm historian, so please.
Yeah.
Yeah, I mean, it's astonishing how small part of time you can measure. It's really for me. But is that attosecond the ultimate unit, or can you go beyond that?
Yeah. The next unit is called zeptosecond. In using the techniques I have shown, in principle, there is nothing limiting you. You can go to the next one. You need to have so the idea here is you have many harmonics. You have a broad energy range, and this is Heisenberg principle. Very large in bandwidths, can be very short in time. So you need even larger bandwidths, and it's possible using a mid-infrared laser to have really very, very broad. The difficulty is to make these harmonics synchronized. But it's more a technological issue than a fundamental one. So in principle, you can go. It has not been done yet. The record is like 40 attosecond.
With optical light?
Yeah, with optical light. I think with free electron laser, they are still a few hundred attoseconds. It's about making the electron bunch leading to the light. Very, very compact. Yeah.
Thank you very much.
Thank you.
Really enjoyed it.
It was okay? Yeah?
Just perfect.